Okay, we're going to continue on here, chapter 7. Last time we got just a little bit into chapter 7. We talked about really a little bit about redox reactions. And as I mentioned last time, there's kind of two sort of big classification or umbrellas that most reactions will fall under. One is a double displacement reaction. Which has the general sort of formula of really two ionic compounds together. And that's really how you recognize it as a double displacement reaction. And as we'll talk about, as we might have talked about a little bit last time, what always happens in the situation is the two positive guys basically will switch partners. And the result of that is you will make two new ionic compounds on the product side. And C and D, C and B. Now, double displacement reactions really account for two of the three reasons why a reaction takes place, and that is either maybe one of these guys will make a solid, and that is sort of the formation of a solid. And the other sort of reason that a reaction takes place is maybe one of these guys actually makes water. So the formation of water, the formation of a solid, which is a precipitation reaction, is really two of the three reasons why a reaction really does take place. Pretty much all the other sort of reactions fall under the big umbrella of a redox reaction. And as we talked about a little bit last time, redox reactions are basically oxidation and reduction reactions. And oxidation means that you lost electrons. Reduction means that you gain electrons. And redox reactions are really pretty much your synthesis combination, your decomposition, your single replacement, and combustion type reactions. But they really all account for that electron transfer that is basically occurring. So those three things, pretty much all reactions pretty much boil down to one of those three things happening. You got an electron transfer, you got a solid being formed, or you have water basically being formed. When we talked about oxidation and reduction, when things do lose electrons, they do become more positive. And when things sort of gain electrons and go through reductions, they become more negative. So we talked about a simple sort of number line you could kind of use to figure out what is being oxidized and what is being reduced. And you could really look at the substance on the left-hand side of the arrow and kind of the same element on the right-hand side of the arrow. And you can look at what's really referred to as the oxidation state, kind of like the charge, but a little bit different. But if you see that particular, for example, element becoming more positive as it goes from the left-hand side of the arrow to the right-hand side of the arrow, kind of moving this way in terms of its oxidation state, that is something that is going through oxidation, is becoming more positive. Vice versa there, if you look on the left-hand side of the arrow and then the right-hand side of the arrow, and you see a substance that's becoming more negative as it goes from left-hand side to the right-hand side in terms of really its oxidation state or number, and moving sort of in this direction along the number line, that guy is going through reduction. So that's a really sort of easy way to figure out what is being oxidized and what is being reduced. They always occur together. So if you can sort of identify one thing, what is being oxidized or what is being reduced, then by default, the other guy is going through the opposite sort of process. So you never have it occur just an oxidation without a reduction. And that's because electrons are being transferred from one place to the next. So they both got to have sort of a change in terms of their electrons as a result of this process. Any questions on that there? Okay, so we're going to go back to kind of the beginning here of the notes for chapter 7 and kind of roll through. We're going to first go back and talk a little bit about reactions in aqueous solutions. So first off, aqueous solutions are those guys that have the AQ symbol next to it. And really a solution is made up of two parts. There's the smaller part of the solution, which is the solute. And there's a larger part of the solution, which is the solvent. So the solute is the smaller part, the solvent is the larger part. So for example, if you took water, which is a liquid, and you add some solid sodium chloride to it, those sodium chloride there will dissolve in the water, and you will get a sodium chloride solution that gets the aqueous symbol next to it. Now, in this case, the sodium chloride is our solute. It is the smaller part, usually dissolved. Water here is our solvent. We'll talk about water is a really good solvent in a lot of cases, especially for ionic compounds. It's not necessarily a good solvent for everything, but definitely anything that's ionic, water really works as a really good solvent. So if you do have an ionic compound, you could probably make a pretty educated guess that the solvent would be water. But again, if it's something different, maybe not ionic, water may not be the best solvent. Water is a good solvent because obviously it is non-toxic, and it does react really well with things that are ionic, and it acts really well with things that are polar as well. If you're not sure what the solute of a solution is, it is always the name of the solution. So here I have a sodium chloride solution. Sodium chloride would be the solvent. If I had a potassium nitrate solution, potassium nitrate would be the solute. So the solute is always the name of the solution. And again, the solvent in a lot of cases is water. So there are certain things that are electrolytes, and electrolytes, again, are substances that when they do dissolve in water, they are able to conduct electricity. And really the reason that the electrolytes are able to conduct electricity is there is the presence of ions. So ions are formed. And those ions, the cations, the anions, positive, negatively charged ions, are the ones that help sort of complete the circuit, if you will, and make sure it can conduct electricity. There are non-electrolytes, which pretty much will stay together. They will dissolve, but they will not produce any ions. And really, because they don't produce any ions, it is basically not going to conduct electricity. So in this case, does not produce ions. So there's a couple of different types of electrolytes. There is a strong electrolyte, and a strong electrolyte will 100% break apart in solution into ions. So there's no whole unit still together. So these are some examples. A lot of ionic compounds are strong electrolytes, like sodium chloride, potassium iodide, calcium chloride in this case. So what that means is if you had a solution of sodium chloride, when it's actually in the solution and you pour some into like a beaker, for example, you have 100% of these ions floating around. There is none of these guys still together. So none of those guys are in the solution. So basically, if you looked at your beaker there, you basically got a bunch of sodium ions floating around, got a bunch of chloride ions floating around, but you have none of the whole unit still together. And that's why it's considered a really strong electrolyte. The production of all those ions, a very common experiment is a lot of times you hook up a light bulb to some electrodes and you put it into the solution. And if you did that in this case, if you put it into a strong electrolyte solution, the light bulb would go off very brightly. So it would turn on, it would be really, really bright because there is a lot of ions that are basically floating around that solution. So whenever you have anything that's a strong electrolyte, it will 100% be broken apart into ions in solution. You'll never have any of the whole units still together. Commonly as well, strong acids and strong bases are also strong electrolytes. So if you have a strong acid in solution or a strong base in solution, it also will 100% break apart into ions. And that's really why it is considered a strong acid or a strong base. Something like hydrochloric acid will completely break apart into H plus and Cl minus. So in solution, you have 100% of those ions floating around. And basically what makes something an acid is the ability to produce these H pluses. So because it will completely break apart, you have a lot of H pluses in that solution, and it's a strong acid and also a strong electrolyte. Now, there are weak electrolytes that will mainly stay together. So, for example, hydrofluoric acid, which is another acid, it's actually a weak acid. And when it breaks apart, it will break apart into H plus and F minus. The difference here between, say, this and hydrochloric acid, which is a strong electrolyte, is in solution, this is mainly what you have. So in solution, you mainly have everybody still together. It will produce a little bit of these guys. So if you kind of were to look at your picture, you would mainly have HF kind of floating around in that solution still together. But you will produce a little bit of some ions floating around with it. So because it's still able to produce some ions, if you were to sort of take that light bulb example and again put it into this solution, the light bulb would turn on, but it would be very, very dim. So it would still be able to conduct electricity. It almost looked like the light bulb's dying. It has just a little bit of sort of power coming to it, but it can conduct electricity really nowhere near a strong electrolyte, again, because of the difference in the ions that are in solution. The other way that you could typically recognize a weak electrolyte is these reversible arrows. And that means that this reaction has really two directions. It has a forward direction, which goes towards the products. And what happens in this reaction is at some point when you gain enough products, they will actually recombine and kind of go the other way and make some reactants. So that is what is referred to as going in the reverse direction as you head towards the reactant side. What happens is, and you'll learn more about this in Chem 1B, you'll reach what is referred to as chemical equilibrium. And what that means is as fast as it goes to the product side, those guys recombine just as fast and goes back to the reactant side. So the rate of the forward and reverse reaction will actually equal each other. And that's what happens in a sort of reversible sort of reaction like this. Now, that is definitely one way that you can for sure recognize it. Outside of some of our strong acids, you can pretty much assume that most acids will be more of a weak acid. Again, some strong acids, which are strong electrolytes, are hydrochloric acid, nitric acid, sulfuric acid, perchloric acid, hydrobromic acid, and hydriodic acid. So this is a little list of some strong acids, which are strong electrolytes. So very commonly, if you do see these guys, they're going to 100% break apart. Like I said, pretty much any other acid outside of that list, it's probably a safe assumption to assume that it's a weak acid and also a weak electrolyte and will mainly stay together. The last thing is like a non-electrolyte, which does not produce. It does dissolve, but does not produce ions. And because it doesn't produce ions, again, it will not conduct electricity. So again, sugar, for example, is an example that we know we could take some sugar and dissolve it in water, and we will get the sugar to dissolve. But sugar is really a molecular compound containing carbons, hydrogens, and oxygens, which means they are going to be sharing electrons. So there's going to be no production of any ions, and it's really that lack of ions which prevents it from really conducting electricity. So strong electrolytes 100% breaks apart. Weak electrolytes pretty much stays together, breaks apart a little bit. Non-electrolytes, again, will dissolve and not produce any ions. This is going to be really important in terms of some of the types of equations that we'll have to write for double displacement reactions, for example, to have an understanding of that. Any questions on the differences there? By the way, if you put the light bulb into a non-electrolyte solution, the electrodes, the light bulb would not go on. So there wouldn't be no power to the light bulb or anything like that. Any questions on that there? All right. So as I mentioned earlier, water is a really effective solvent for a lot of things, especially especially for ionic substances, also polar substances as well. And that's really because water itself, if you remember from bonding, is a polar molecule. That means there are really two sides to water. There is the oxygen side that's more negative, and there's the hydrogen side that is more positive. And that works really well for ionic compounds because when you go to dissolve something that's ionic, pretty much they are sitting here in an ionic solid such as this in kind of a three-dimensional space. So what happens is when you go to dissolve something that's a solid in water, you typically do two things, right? You start to stir it. That throws a bunch of water molecules all over that solid. It also increases the energy as you're stirring it, right, to get it to dissolve. And what will end up happening is that will allow enough water molecules basically to kind of rip these ions apart from each other. And when that happens, we will end up with, say, a positive ion that will be attracted to the negative side of water, which is the oxygen. And we'll have a negative ion that would be attracted to the positive side of water, which is actually the hydrogen in this case. And that again does two things. It allows really that solid to dissolve. And at that point, we visually cannot see it anymore because it is surrounded by a ton of water. So it looks like it's gone. It looks like maybe it reacted away or something like that. But you know that it is actually still there, right? So when we make a solution, it's really a physical process. You know that from some earlier experiments. If you remember, you had those earlier ones where you put your solution on the evaporating dish and you heated it up to evaporate off all the water, and then a solid came back, right? And that's what happens here. We just can't really see the sodium or the chloride, for example, if that was the solid anymore because it's surrounded by so many waters. But if we did, again, put that sort of solution back up on an evaporating dish and started to heat it, all of our water, right, would evaporate off. And that would allow these two ions basically to come back together, and you would once again sort of see the solid reform. So water works really well with ionic compounds because all interaction, simple interaction of positive, negative sides. So positive side of one attracted to a negative side of the other. So because water really has a positive and a negative side, works really well as a solvent for ionic compounds because there's positive ions and negative ions, makes it really interact really well with it. And that process, again, is sometimes referred to as hydration, where we sort of dissolve the ions in water. We're basically hydrating them by adding water to it. Any questions on that there? So as I mentioned before, acids and bases are also electrolytes. And there are those strong acids that I listed a second ago. And again, those are really good ones to know. They will 100% break apart. So our hydrochloric acid, again, 100% of what you have in solution are these ions. And by the way, the general definition of an acid is something that has the ability to produce H plus or H3O plus, which is the hydronium ion, in solution. So the ability to produce H plus or H3O plus in solution is what an acid is. A base, on the other hand, the basic definition of it is the ability to produce hydroxide ions in solution. So free hydroxide ions in solution is really kind of your basic definition of a base. So things like sodium hydroxide, when it breaks apart, will break apart into Na plus and OH minus, produce a bunch of OH minuses, which is why it's a strong electrolyte. This is another example of a weak acid. This is acetic acid, which is basically your major component there, vinegar. In solution, you basically have the acetic acid still together. So that's mainly what you have. but you do have a little of these guys that are formed. So since you still are forming a little bit of H plus, acetic acid is still considered an acid because it has the ability to do that. It will not be able to produce anywhere near the H plus something like hydrochloric acid would be able to produce. Obviously, that reversible reaction, again, we see with our weak acid. Our strong acid is really a one-way street, going to all break apart into the product side. Nothing is coming back the other way. So it's all just going to basically dump out over there into the product side. So let's first then talk about precipitation reactions. And precipitation reactions are a really more specific definition or classification of the double displacement. So again, the double displacement is your big umbrella for with a more specific classification being that precipitation reaction. So in this case, when we have our two ionic compounds, which these guys will switch partners. One of these guys will end up making a solid, which is known as a precipitate, sometimes abbreviated PPT for precipitate. So let's take a look at one here, or an idea. A precipitate is a insoluble solid that forms as a result of mixing a lot of times two solutions together, which you'll do today in lab. You'll mix a couple of solutions together, see if it gets a solid that forms. In reality, a solid has to be like a rock hard solid that just like drops to the bottom of the beaker or whatever it may be. It could be it got cloudy, you know, it got a little mushy, some stuff that wasn't there that before you kind of mix the two solutions together. Precipitation reactions usually involve ionic compounds. And it's always that sort of double exchange that occurs where the positive guys basically will switch partners. So if we take a look at this reaction here, this is the molecular equation, and this is lead to nitrate plus some sodium iodide, makes some lead to iodide plus some sodium nitrate. I don't know if the 2 made it onto your notes or not, but there should be a 2 there. I think it got lost somewhere. So this is the molecular equation. So basically, these are two solutions, lead to nitrate to sodium iodide. We're going to mix together. Now, when we mix it together, most strong electrolytes that are ionic are pretty much just ions. So we're basically taking a couple of ions and sort of mixing them together. And in this case, you know, you basically have some lead 2 guys floating around. You got some nitrate floating around, and the other sort of container, you got some sodium ions floating around, and you got some iodide ions floating around. So you're going to kind of mix both of these together. So you really have 4 different ions sort of floating around. And what's going to happen is, again, the positive guy on one side is going to switch over to the negative guy on the other. That is why when we put these guys together, that's a sodium with a +1 charge and a nitrate with a -1 charge gives us our proper formula. And over here, that's a lead with a 2+ charge and an iodide with a -1 charge, which gives us our proper formula over here. In this particular case, that combination, when the lead and the iodide come together, will make the solid that we would see in this case, this sort of yellow solid. We could actually write another equation which actually represents what is going on when we sort of mix everybody together, and because these guys are solutions. So most ionic compounds like this are strong electrolytes, which means it will 100% break apart. So we could take that first guy, which would be lead 2 ions, is really what it is. There are 2 of these nitrates, so that does come to the front. So we would bring the 2 to the front and tell us that we have 2 of these nitrate ions. This guy here is a strong electrolyte as well, which means it will break apart. And that 2 gets distributed to everybody behind it when we break it apart. And we would end up with 2 of the sodiums and 2 of the iodides. Coming to this side, this is a solid. Now, the only way for a solid to be a solid is the positive guy and the negative guy, they have to stay together. Pretty much all solutions are ions floating around freely. So in order to make a solid, you got two that has to kind of stick together and drop out and make the solid. So when we write this type of equation, anything that is a solid, we don't break apart, we do keep it together. Otherwise, it would not be a solid. Typically speaking, when you write this type of equation, which we'll talk about what it is in just a second, you keep together anything that is a solid, anything that is a liquid, occasionally a gas, if you should come across a gas, and anything that is a weak electrolyte. So anything that's a weak electrolyte, a solid or a liquid, you actually keep together because that's really how they are in the solution. The sodium nitrate here is a strong electrolyte, which means that 2 would also get distributed to each of those guys, and that would give me 2 sodiums and 2 nitrates. This equation, which represents really what's happening when everybody goes for a swim together, is what is sometimes referred to as the total ionic equation. Some people call it the complete ionic equation. I think your lab manual just straight calls it the ionic equation. So that's all the same thing here, basically. So this is a equation that represents what happens when you mix everybody together. It's a ionic equation, which means if you write the formula for ions, which you should in this case, they should have charges, yeah? And everything should be balanced. So you do need to distribute the coefficients from the molecular equation in front of all those ions when you drop down to your total ionic equation. When you get to this equation, you can look on the left-hand side of the arrow and the right-hand side of the arrow, and you will be able to find ions that look exactly the same on both sides. So for example, here, if I look to the left, I have 2 nitrates. And if I look to the right, I have 2 nitrates. If I look to the left there, I got a couple of sodiums. If I look to the right, I have a couple of sodiums looking exactly the same on both sides. These guys that look the same on both sides, they actually will cancel each other out. These guys are what are referred to as spectator ions. And if you are a spectator, you're pretty much watching what's happening. You're really not participating. And that's the idea here, is basically watching. They're not really participating in the actual product that's being made in this case. So they're still there floating around, but they're really not making anything. They're just along for the ride. They're along to balance out the charge. So for spectator ions, we cross them out on both sides. And what that leaves us is the third type of equation, which is important. And this equation basically tells us when we throw these two solutions together, what is really happening. And what is really happening is it is the lead from the lead to nitrate swimming around and finding the iodide from the sodium iodide to come together to make this solid. So this is like cutting everything out, just the basic. This is actually what is occurring when you put these things together. This is what is known as the net ionic equation. And as we see here, this is really what's happening. We're making a solid, which is a precipitate. Why it's called a precipitation reaction. And again, one of the reasons why a reaction takes place is the formation of a solid. Question on that there. Let's take a look at one here, perhaps. So let's say we do one, maybe we did the other day, maybe we'll do today. That is not it. That's an A and an N. Let's try this again. There we go. All right, take a little silver nitrate. The guy in those brown bottles, plus some potassium chloride. This again is a double displacement reaction, positive, negative, positive, negative. Again, our guys are going to switch partners. That's going to give us a silver and a chloride, which will be a solid, and a potassium nitrate, which would be aqueous in this case. All right, so take a moment or two, write the total ionic equation and write the net ionic equation for that reaction there. Okay, let's take a look. So again, this is going to be a strong electrolyte, so we're going to break this guy apart. So that is going to be a silver ion. And our other guy there is our nitrate ion. Potassium chloride, also a strong electrolyte, which will break apart into one potassium that has a +1 charge, and our Cl, which is group 7, has a -1 charge. Our solid here, as we've been talking about, we will keep together and not break it apart. That will give us our silver chloride. And our potassium nitrate, again, most ionic compounds probably that are aqueous is probably going to be a strong electrolyte and break apart. So that would give us a K plus and a NO3 minus in this case. At this point, that would be our total ionic equation. Again, our ions have charges. We are going to look at this guy here and find our spectator ions. And in this case, it is the nitrate. And it is the potassium in this case. Remember, they do need to look the same on both sides. They do need to have charges because they're ions. And you should have the same amount on both sides. If you ever find yourself at this point where you have not the same amount of ions on both sides, you frankly messed up on the balancing part. So something's not balanced correctly. So they should always completely cancel out. In this case, these guys being our spectator ions. Going to cancel. That again is going to leave us our net ionic equation, which tells us exactly what's happening in this reaction. It is that silver ion from the silver nitrate that's going to find the chloride ion from the potassium chloride and form that solid silver chloride. And that again would be our net ionic equation. Any questions on any of those parts there? Okay, so let's take a look here. I think some of these slides are what we just went over, so I'll just slide them across. All right, so there's our total ionic equation. These are our spectator ions. And then obviously canceling out our spectator ions gives us our net ionic equation. All right, so the question might be, how do we know when we put together certain ions to form an ionic compound, would we expect a solid to form or not a solid to form? And that's really what solubility and our solubility rules are for. Solubility helps us predict whether or not we would expect a precipitate to occur. If something is soluble, that means that it is going to basically dissolve, right? You would not get a solid. If something is insoluble, that means when you put it together, you do expect a solid to form. So if something is soluble, it typically will get the aqueous symbol. And if something is insoluble, it will get that S symbol or solid next to it. There are some solubility rules we're going to look at here in a second. And you might remember there's also, you come across a solubility in an earlier lab. It was like way out of place, way early. It was at a table where you kind of move your fingers together to 2 element names and it'll say, you know, either soluble or insoluble in there. Basically, solubility tables are broken up into a couple of categories. One is soluble, and that means if you put those guys together, you would not get a solid. And those are the guys that should get the aqueous symbol. The other really main category of a solubility table is something that is insoluble. So when those ions come together for ionic compounds, you would expect them to basically stay together and make a solid. So those guys get the solid sort of treatment. Not too much used a lot of times anymore, but there are things that are sometimes considered slightly soluble. And for the most part, slightly soluble really does sort of lean towards more being insoluble. So most of the time it kind of leans in that direction as being a little bit more insoluble than soluble. Everything, by the way, and you'll learn if you continue to take chemistry and Chem 1B and all that kind of stuff, everything, even if it's based on solubility rules, considered insoluble, there's always a little bit of it that's able to basically break apart, even if it's a super, super small amount, will break apart. But a majority of it, if not almost 99% of it, will stay together, which is why it's considered insoluble and a solid will form. But even things that technically are insoluble have some degree of solubility, just a super, super small amount. So let's take a look at some solubility rules here. These are things for ionic compounds that are typically soluble. So these are guys that typically would get the aqueous symbol if they are soluble. If you see in your formula anybody from group 1 on the periodic table, sodium, a potassium, a lithium, you don't need to look any further. They are soluble in all situations. They should get the aqueous symbol next to them. So definitely should get the aqueous symbol. If you see in your formula ammonium present, there are no exceptions. They also should get really the aqueous symbol next to it. If you have any ionic compound that contains nitrate, chlorate, perchlorate, you can even add acetate to it if you like. Those guys are also going to be soluble. There are no exceptions. So pretty much if you come across a chemical formula and you see any of those guys in it, you don't need to look any further. You could just put the aqueous symbol next to it and know that it should be a solution. There should be no solid that would be formed. Things that have chloride, bromide, and iodide, they are going to be solid. They're going to be soluble as well. But there are some exceptions, and that is these three right here. So if you have a chloride, a bromide, or an iodide that contains silver, that's mercury 1, and that is lead 2 in it, it is actually going to be opposite of soluble, which means they will be insoluble, and you would give it the solid symbol next to it. So those are some exceptions to things that are normally soluble. Most sulfates are going to be soluble, which is aqueous, except if you have calcium and silver sulfate, which are slightly soluble, and barium, mercury 2, and lead sulfate, which are insoluble. So these guys would be a solid in that case. So most of the things listed here are going to be aqueous. They're going to be soluble. No solid would form unless you hit any type of exceptions to any of those guys. And again, there are some that have no exceptions, so you don't have to go any further than those things. Any questions on that there? Yeah. Except with here? Yeah. Yeah, so if you have anything that has Cl in it, anything that has Br in the formula or I, in most cases is going to be soluble. The only time that those three guys would not be soluble is if they have either silver, lead, or mercury there. So it'd be the opposite. So there are exceptions to them being soluble. They would then turn to be insoluble and would be a solid at that point. Other questions? Now, there are certain things that are typically insoluble. So these are some things that typically would be solids. Hydroxides are typically solids, except if you have group 1 involved. And then they would be aqueous. So it's kind of the exception there. And it's really the same rule as the previous slide. The previous slide was all group 1 is soluble. So in this case, same rule applies. If you see group 1, even if it's with hydroxide, it's going to be soluble. So it kind of supersedes it. Carbonates, phosphates, and sulfides are insoluble, which typically should be solid, except if it is group 1 or ammonium. And again, those guys then would be aqueous. So most of the ones listed here should be solids, unless it's basically group 1 on the periodic table or ammonium present, then it would be soluble at that point. So sort of the opposite is true. All right, so for example here, let's say we took iron (3) nitrate plus some sodium sulfide. All right, do two things here. Finish up the equation and use solubility rules to determine are they aqueous or solids. So finish the equation and balance it, and then determine the solubility of each of these guys. It is a double displacement reaction here. Yes. So since you see it's this sort of double displacement situation, you know that these two guys are going to switch partners. You want to make sure that when you do predict the formulas on the other side, as we might have talked about previously, that you actually do get the right formulas. You do not want to balance and predict the formulas at the same time. So our iron here, the basic unit of our guy on the left there, is really an iron with a +3 charge. And even though there are 3 of these guys, it doesn't matter at this point. The basic unit of nitrate is NO3-. Here, the basic unit of sodium is group 1, which means it's a +1. The basic unit of sulfur, which is group 6, is a -2. That is what you want to use when you put them together to write the correct formulas, like you were doing nomenclature. The iron would then go with the sulfur, and the common number there is 6, which means Fe2S3 would be the proper formula. The sodium here is +1. The nitrate is -1, which means you just need one of each of those guys, and that would get you NaNO3. Any questions on that there? Now that you have the correct formulas down, you want to make sure that you balance it at this point with coefficients. So it looks like, let me just kind of clear up some of this here, I think. My scribble. Okay, so to balance it, it looks like perhaps we need probably 3 of those. That gives us 6 sodiums, gives us 6 nitrates, which means we need like a 2 there, I think. Yeah. So we do have a balance at this point. Now that you have a balance, we can now use our solubility rules to help us decide. So looking at the very first one, although we may not see iron there, we do see nitrate. And if you look at the solubility rules on the previous slide, nitrates are soluble in everything. There's no exception, which means definitely going to be aqueous. Yeah. In this case, we look at sodium, which is group number 1, and that is also soluble in everything. Don't need to look any further. That is going to be aqueous as well. Coming here, that is iron, which we might not find, but we can find sulfide, which is this guy. And that is insoluble. And the only exceptions are group 1, and iron is not group 1. So this would still be a solid in this case. Looking at sodium, pretty much as far as I need to go because that's group number 1. It will be aqueous. You could also look at nitrate in that case if you wanted to, and it would tell you the same thing. Question on how to use that solubility rules. That is also why earlier when we did the other example, which I think was silver nitrate plus some potassium chloride, made some silver chloride and some KNO3. Looking at this one, although we don't see silver, we see nitrate, which is soluble in everything, so we know that is aqueous. I see potassium, and that really is as far as I need to look because it's soluble in everything. I see silver, but I do see chloride. Remember, chlorides are soluble in everything except for 3 exceptions. And the 3 exceptions for chloride is silver, lead, and mercury. And in this case, that would be an exception. So instead of being soluble, it's going to be insoluble, which is how I knew that guy was the solid in this case. And lastly here, potassium is really as far as I need to go. I could look at nitrate as well in this case, and it would tell me that it is soluble as well. Question on how to use solubility rules. Okay. Now, we talked a little bit about acids and bases earlier, but just to officially sort of talk about it here, acid and bases. Acids have a sour taste. They do turn litmus paper different colors. You might have used litmus paper the other day in lab. Acids will typically turn litmus paper red, or keep it red if it's acidic. They react with metals to form hydrogen gas. Also did it the other day, I think, with magnesium hydrochloric acid. Put your thumb on the test tube. Bunch of gas coming right, light the wood splint. Those bubbles is the hydrogen gas that occurs. And aqueous solutions of acids can conduct electricity because you could have strong acids and you can have weak acids, both of which produce ions and both can conduct electricity. Once again, acids, the ability to produce H plus in solution. Bases have a bitter taste. They feel slippery. A lot of soaps are bases. A lot of like drain cleaner, that type of stuff is also bases. Bases change litmus paper actually blue. So that's what you probably saw the other day when you did it. You took some calcium and some water. You made some calcium hydroxide, which is a base. Should turn your litmus paper blue when you touched it on it. And strong bases and weak bases also will conduct electricity. And once again, a base is something that can produce hydroxide ions there in solution. So earlier, I again put up that list of sort of the strong acids. And as you go through your chemistry career there, it's good to remember those strong acids. So once again, hydrochloric acid, nitric acid, sulfuric acid, perchloric acid, hydrobromic, and hydroiodic. Those are all strong acids, strong electrolytes, 100% break apart. So if you had a solution of nitric acid, floating around in that nitric acid is just going to be those H pluses and nitrate ions floating around. And again, because it will create a lot of those H pluses really quickly, that is why it's considered, again, a strong acid. Bases, on the other hand, again, produce hydroxide. And a lot of our strong bases have actually hydroxide in the formula. And if you go to the periodic table, group 1, like around sodium, come down to potassium, hang a right to calcium, come down. Any of those guys that have hydroxide in its formula are typically where your strong bases come from. That's because group 1 on the periodic table is the alkali metals. Group 2 on the periodic table is the alkaline earth metals. And as you might imagine, the word alkaline means basic. Yeah, so that is where a lot of our strong bases actually come from, is group 1 and 2 on the periodic table, that they have hydroxide, like sodium hydroxide, potassium hydroxide, and so forth. If you had a beaker of sodium hydroxide, it would 100% break apart into sodium ions and hydroxide ions and produce a lot of OH minus really quickly. In terms of acids as well, just a reminder, I think I might have mentioned it, but again, H plus and H3O plus are really the same thing in terms of acid-base chemistry, and this has to do with acids. Yeah. So acids have the ability to produce H plus or H3O plus, and they're sort of interchangeable, H plus and H3O plus, which is the hydronium ion. So what happens when we react a strong acid with a strong base? This type of reaction is sometimes referred to as an acid-base neutralization reaction. It also falls under the double displacement umbrella. Any combination of a strong acid and strong base that you put together, the overall reaction that is actually taking place is really the formation of water. And the net ionic equation that you will get for any combination of strong acid and strong base is the H plus from the acid reacts with the OH minus from the base to make water. And a reminder that making of water is one of the 3 reasons why a reaction takes place. So that is basically what is happening in this case. Similar to what we were just talking about with precipitates, the formation of a solid is, again, one of the reasons why a reaction takes place. So if we took hydrochloric acid plus some sodium hydroxide and reacted together, this is our molecular equation. We could also, because this is a strong acid, know that it will 100% break apart into H plus and Cl minus. Sodium hydroxide, which is a strong base and a strong electrolyte, will also break apart into a sodium ion and a hydroxide ion. On the right-hand side, we will make water. Water is a pure liquid. It is sharing of electrons, will not break apart, will stay together. And remember, anything that's a solid, a liquid, or a weak electrolyte stays together. Sodium chloride is a strong electrolyte, will break apart. And this would be our total ionic equation here for what is going on. We could find our spectator ions. We have a chloride on the left, a chloride on the right, a sodium on the right, a sodium on the left. Those are our spectator ions here. And these guys cancel, leaving us our net ionic equation of H plus OH minus, making H2O. So again, no matter what combination of strong acid or strong base that you put together, that is ultimately what is occurring. You're going to make water as a result of it, which again is why it's sometimes referred to as an acid-base neutralization reaction, because basically water is being made. Whenever you take a strong acid and strong base together, you got an acid, you got a base, you always make water. And you always make what is referred to as a salt. And a salt is just an ionic compound. So you always make sort of salt and water in this case. Any questions on that there? Basically what just did. So as I mentioned before, in addition, you will make a salt. So in these cases here, these are our acids, these are our bases, these are our obviously water, and each of these are our salts. I would say in most cases, the salts that you form in a reaction of a strong acid with a strong base, in most cases will be soluble. They could be insoluble, but in most cases, they're going to be pretty much a soluble salt. And really water is going to be flowing around. All right, any questions on double displacement reactions? So we're going to talk about the other types of reactions, which really all fall under this redox reactions that we talked about last time. And again, a reminder that an oxidation loses electrons and a reduction gains it. And again, you can remember that as the Leo the lion goes grr, loss of electrons, oxidation, gaining electrons, reduction are the oil rig. Sometimes people like to remember that oxidizing is losing, reducing is gaining. So if we look at something like sodium chloride, which we might have looked at, I think perhaps at the very end last time, but just in case, remember, you could look at sort of the changes in what is really referred to as the oxidation state. Again, a little bit different than the charge. Remember that any element that is by itself, not combined with anything else, will pretty much have an oxidation state of 0. So sodium all by itself is 0. Chlorine in this case is naturally the way it comes. Remember, it comes as a diatomic molecule, so that is how it naturally comes. It is only when the sodium and the chlorine get together that they do gain a charge. Sodium has a +1 charge. Cl has a -1 charge. So again, you could use that little number line to help you figure out. If we look at the sodium, started at 0, ended at +1, becoming more positive, which means here sodium is being oxidized or going through oxidation. Chlorine started at 0, ends at -1, which means it's becoming more negative and going through reduction, which means it is being reduced or going through reduction. Again, if you can figure out just one, the opposite is happening in this case. This is always what should happen when a metal and a non-metal get together. If you remember when we talked about naming and bonding and all those things, it is always the metal that loses electrons to become positively charged. It's always the non-metal that gains electrons to become negatively charged. So you should always see that with a metal and a non-metal, which is that electron transfer from the metal to the non-metal. And once again, the electron transfer in this case is the third reason why reactions take place. So ultimately, all these reactions will have some type of electrons being transferred, which is why they do take place. Any questions on that there? All right. Thank you. All right, that is the oxidation reduction reaction here. Here's another example. This is magnesium and oxygen, which you did the other day when you burnt the magnesium ribbon. Hopefully you didn't look directly at it. Magnesium by itself has an oxidation state of 0. Oxygen, that is naturally how it comes. It has an oxidation state of 0. When the magnesium and the oxygen get together, magnesium makes a +2, oxygen makes a -2. So once again, magnesium started at 0, ends at +2, becoming more positive, which means it's going through oxidation. Oxygen starting at 0, becoming -2 to the right-hand side, becoming more negative, which means it is going through reduction. These are what are sometimes referred to as half reactions, which can show what is happening in the oxidation step and also what is happening in the reduction step. And we'll take a look at it on the next page. I think it has a better setup of it. So those are called half reactions. And one thing when you do write half reactions, which we probably won't do too much in here, but electrons should be on the product side in the oxidation reaction, like they're being lost or given off. And electrons should be on the reactant side in the reduction reaction, like they are being gained, basically, in this case. We're not going to worry about nonmetals for now. We don't come across too much of it here in regular chemistry. So let's talk about other ways to classify reactions. So we have really our two big umbrellas of double displacement and redox reactions. And as we've been talking about throughout this chapter here, really those are the three reasons why a reaction takes place. We made a solid, we made water, or we transferred some electrons. So as we saw earlier, a precipitation reaction is a double displacement reaction. Again, this is another one, positive, negative, positive, negative. Once again, our guys switching partners on the other side, where our potassium ends up with the nitrate, and in this case, our barium ends up with the chromate. It is considered a precipitation reaction because a solid is formed. This, by the way, is not an oxidation reaction. So this is not a redox reaction. Nobody's changing charges or anything like that. Just to show that to you, potassium is +1 there, potassium is +1 there. He's +2, he's +2, this is -2. And this guy is -2, that's -1 and -1. So there's absolutely no change of electrons in a double displacement reaction. It's only in those redox reactions where we see that occur. As you can see here, we switched partners, and that is how you recognize that double displacement as we've been talking about. Always the positive guys switch partners. Make sure, as we did talk about, that you get the proper formulas first and then balance it. So regardless of the balancing aspect of it, if you have to predict products, Always get that formula correct first. We also saw this, also double displacement reaction. Again, hydrochloric acid, positive, negative, positive, negative. In this case, when our positive guys switch partners, we get our water like we expect, and we get our salt that forms here as a result of that. So again, those two reactions demonstrate the solid formation, the water formation. And now we're going to obviously talk about our oxidation reduction reactions. The first sort of more specific classification of a reaction is a single replacement reaction. And a single replacement reaction is a little different than a double displacement reaction. You only have actually one ionic compound. And this ionic compound is usually reacted with a metal, for example. And the metal actually has no charge to begin with. But when a metal does get a charge, it is actually going to be a positive charge. So what will happen is the metal that normally will be a positive will kick out the positive guy and make a new ionic compound where it gains a charge. And the guy that gets kicked out actually will end up with no charge on the other side. We actually saw this occur in lab early on when you did those halogens and the different layers and one guy going from one layer to the next layer. You could do this with a non-metal as well. And non-metals usually will make a negative charge. So he will actually come and kick out the negative guy. The result of that is a new ionic compound when that guy becomes negative. And the guy that gets kicked out will end up with no charge. So that is what we see here with zinc and hydrochloric acid. It is also what you saw with magnesium hydrochloric acid that we were just talking about, where you put your thumb on the test tube. This guy has no charge. This guy is +1. This guy is -1. This has no charge. That is +2 and -1. The zinc is going to come in and kick out the hydrogen. The result of that is hydrogen gas, which is the bubbles that come. At that point, the zinc gains its normal +2 charge that hooks up with chloride that has a -1 charge to give us our zinc chloride here that we end up with this part. This is a single replacement reaction. It is also still a redox reaction. If we look at the zinc, zinc started at 0, ended at +2, became more positive. The zinc is being oxidized. It is actually, in this case, the hydrogen. Hydrogen on the left-hand side started at +1, ended at 0, moving in that direction, becoming more negative. It is the hydrogen here that is being reduced. What is happening with the chlorine on both sides? It started at -1 and ended at -1. It is actually just a spectator ion. There's nothing happening with it. It actually, what's really happening in this reaction, if you wrote a net ionic equation, is the zinc plus the 2 H pluses makes H2 plus Zn2 plus. So it's really this guy going from 0 to +2, and this guy going from +1 to 0 is really ultimately what is happening in this reaction. So you could classify this reaction, and most people would classify this reaction as a single replacement reaction, but it also does fall under, obviously, a redox reaction that is taking place. Any questions on that? In order for the guy coming in this reaction to occur, the one that is coming in needs to be more reactive than what it is replacing. Otherwise, this reaction would not take place. So A needs to be more reactive than what it is replacing. So for example, if you swapped out the zinc for some copper, not going to happen. Copper is less reactive than hydrogen, so that reaction would not take place. Another more specific classification of redox reactions is a combustion reaction, and these are a couple of combustion reactions. Most people, when they think about combustion reaction, pretty much thinks about the organic combustion, like you did the other day when you burnt the table with your Bunsen burner, perhaps. An organic combustion always has an organic compound, and that usually contains carbon, hydrogen, and maybe oxygen. But what it always has in terms of the other parts of the reaction are these three things: H2O, CO2, and O2 is a classic combustion reaction, usually involves heat. The purpose of why you hit it on the bench was you should have saw some condensation. Yeah, so that's because water is made and you hit it on the really cold bench, cools it back down. You see liquid water for a second before it evaporates off again. That is a combustion reaction. There is a more just general definition of a combustion reaction, which frankly means you just need O2 on the left-hand side. So anything that has technically O2 on the left-hand side is a combustion reaction. But most people will look at the organic combustion reaction, also a redox reaction happening. All right, we just have a couple more slides and we'll finish it up here. So just hang in there. We're going to talk about a synthesis and combination reaction. And this is basically putting things together. So A plus B makes A and B. So two things make one thing is a classic combination or synthesis reaction. Hydrogen and oxygen come together to make water. So two things make one thing in combination or synthesis. Sodium and chlorine come together, make sodium chloride. Now, if we take a look at that reaction we were just talking about there with the magnesium plus the oxygen, making magnesium oxide, you could classify this reaction three different ways. That is two things that make one thing. That is a combination or synthesis. That is a redox reaction, as we talked about earlier, 0, 0, plus 2, minus 2, electrons being transferred. It also could be classified as a combustion reaction because it has oxygen in it. So this one reaction could be classified three different ways. In most cases, it's pretty clear maybe which way you want to classify a reaction, but you can definitely classify the same reaction in multiple ways, depending on what you're looking at. The last type of reaction is really the opposite of synthesis or combination, and that's a decomposition reaction. A decomposition reaction, you basically take one thing and you break it apart into two or more things. So water, like you did the other day with the 9-volt battery, run electrical current through it. You should have saw hydrogen gas and oxygen gas being made. That's a decomposition reaction. Earlier on, when you did like the Alka-Seltzer tablets, you made something like carbonic acid that quickly broke apart into water and some CO2 gas that plop, plop, fizz, fizz bubbles that maybe you remember. It's really the opposite of a synthesis reaction. This is also still a redox reaction. We have the hydrogen going from +1 to 0. We have the oxygen going from -2 to 0. And that is electrons being transferred as well. So to finish up and summarize the different types of reactions and sort of where they all fall, under the big umbrella of double displacement, you have more specific classifications of a precipitation reaction and acid-base reactions, which account for solids and water being formed. Pretty much everybody else is going to fall under the redox big heading, where electrons are being transferred. Those are your synthesis reactions, your decomposition reaction, your single replacement reactions, and your combustion reaction. Any question on any of that there? All right, that wraps up chapter